Good morning. My name is Bruno AMEDURI, and I'm very happy to be here and to attend this webinar. I would like to thank Cedric, Jean-Marie, and other the dream team of organizers for this interesting meeting this morning. So I come from south of France. I know that now in north there are a lot of rain and floods, but we have a milder temperature here, and I'm very happy to report about the new PVDF and VDF copolymers as unique electroactive materials. So just a few words on PVDF. This is, as you know, the second most produced fluoropolymer with a TG of -40, melting point ranging according to a defect of chaining 170 to 180. It's a semi-crystalline plastic, UV and aging resistant, chemical igneous, and it has also some ferro or piezoelectrical properties according to the conditions. So this magic PVDF can be involved in many applications, just like pure water transportation, filtration, energy, chemical processes, wiring cables, polymer additives, and also as coating for architecture, industrial coatings. And indeed, this polymer can be achieved from the monomer. Monomer is vinylidene fluoride, which has a melting point of -140. It's a gas. Boiling point is -82. It's not so well soluble in water, with a critical temperature of 30 and a critical pressure of 44 bars. I think Thibaut will remember very well because he worked a lot in our facilities. So this is the autoclave with valves and manometer. We have also a rupture disc in case of high pressure. So this is under pressure, working with a controller, monitoring the steering and the temperature, and all can be recorded on this screen of this computer device in which we can follow the pressure and the temperature versus time. So VDF can be polymerized under radical conditions and leads to PVDF in which this has been well reported today, alpha phase, beta phase, and gamma phase. And as thermodynamically, you can get the beta phase, but kinetically you have the alpha phase, and major after polymerization, you have a wide variety of alpha phase in the medium with gamma and beta, and also delta and epsilon. So the point is, as this is a crystalline polymer, it is required to investigate the unit cell parameters. And as you can see, Hasegawa 10 years ago, 20 years ago, reported the alpha beta with a crystal forms and led to the A, B, and C parameters of a unit cell. So you have an organization, of course, in the system. The alpha and epsilon are non-polar phase, while the beta or trans leads to a zigzag phase. So probably you are familiar with this system, because if you want to draw to get some beta polymorphism of PVDF, you have to investigate a lot of chemical process or thermal process. You can anneal at high temperature. You can make mechanical stretching from alpha to beta. You can do some annealing at very high pressure and pulling very high electric field. So obviously from melt, it's possible also to have a beta system to get the beta, or if you fail to this protocol, you can lead from alpha phase to gamma phase or delta phase. So this was developed in, let's say, 30 years ago, and then Tashiro also revisited this process and supply some different treatment in order to obtain either from the melt form or from the solution to get basically some beta phase. Drawing at low temperature also is a good possibility, but as you can see, this is very, you have a couple of facilities to process that. So we will go later to see how the DE curves evolves from the stretching or from the pulling or from the high pressure system. What are the different techniques in order to characterize this PVDF? You have a wide angle X-ray scattering, IR, and DSC. Obviously, by DSC, you can see the melting point, but also you can see some Curie temperature, which is not obvious on this drawing. And indeed, Lanceros Mendes in Spain revisited that and did a lot of series of investigations in order to well characterize the alpha phase with frequencies at a couple of here from ranging between 500 to 975, or of course the evidence of gamma frequency of beta phase is 470. You can have also 510 or 840, and for gamma phase you have at 870. So these techniques are very straightforward in order to characterize and to enhance and evidence the presence. Another parameter is very important is the piezoelectric parameter. So PVDF has a piezoelectric coefficient of 33, which is highest for polymers. Polylactide also is about 10. It's rather surprising. Polyamide 113. PZT, so lead, zirconium, titanium, almost 600, which is the king of the piezoelectric parameter. Then barium titanate is not so bad. And also some lithium neogate is 6, and quartz. And applications are very interesting, as mentioned before, by Thibault, by Professor Lu Zhu, organic printing and flexible electronics, actuators, artificial muscles, touch sensors, active flexible electronics, ferroelectric fields, effect transistor, robot. So I would like to also to emphasize on the recent work achieved by Professor Soldera in Sherbrooke University in Canada. Professor Soldera did a lot of atomistic simulation in order to study the influence of the radial effect in the thermal properties PVDF. If you consider the monomer, you have CH2CF2, and CH2 is regarded at the tail, while CF2 is the head. So when you polymerize it, you can have different chaining. You can have, of course, the major head-to-tail arrangement, and then you can have also some head-to-head units followed by a tail-to-tail unit. And of course, these defects of chaining are going to bring some features which can be dramatic for the PVDF. You can decrease a lot the melting temperature or the Curie temperature. And Professor Soldera measured the melting point of alpha phase and beta phase. And also when you have 10% radio defects, so this is alpha phase, okay, when you have simulated 100% head to tail addition. But when you see 10% defects, you have a dramatic effect on the loss of melting temperature, while for the beta polymorphism, the influence of the presence of 10% radio defect is not so critical. On the other hand, he measured the activation energy of PVDF versus the TG, and showed that the higher the PVDF ratio defects, the lower the activation energy, and also the lower the TG. So this shows that probably the presence of defects plays a plasticizer role in the PVDF. What we have done in the lab has been first to investigate some telomers of VDF. So this reaction of telomerization has been developed more than 40 years in the lab. And let's say in the last 25 years, we have done a lot of work on telomerization of free naked monomers. And this, for instance, when you use a chain transfer agent of C613I, You can do, of course, some contra-radical polymerization by iodine transfer polymerization, but also you are going to stop the reaction when you want in order to prepare some well-designed fluorinated polymers. And these applications are numerous. You can have some solvent for lithium batteries, surface modifiers for silicones, for surfactants, macromonomers, nanocomposites, and of course, you can make some thin films and to investigate the ferro and piezoelectrics. And this work started in 2010. It was 33. The remanent polarization was rather high, about 100, and the ferroelectric properties with remanent polarization of 90 millicoulomb per meter. So this has a behavior of a ferroelectric compound, but this was for us the first beginning of fibers in order to prepare some beta polymorph system. Another one was very surprisingly using some eggshell. So they boiled the eggs and took the shell, and they crush it and make a mixture with mormonite and PVDF. And as you can see, according to the content of eggshell membrane, they could increase slightly the presence of beta phase up to 80%, which is not so bad. So this was very well identified by X-ray diffraction, and also the power input versus the content of eggshell could reach rather high voltage, high power, sorry, at 40% of eggshell. So this was published by an Indian group 2 years ago. The beta phase, alpha phase, and gamma phase, and also by a wide-angle XCL scattering. So this chart is very interesting. I think it has been shown by Jean-Marie in the previous state. And you can see here that the sample was alternating field. You have some nice, different fast TSC cooling. You can see that you have different behavior regarding the alpha phase of a co-crystallization of alpha and beta phase or beta phase in certain conditions. So you have to cool at very high temperature speed, and you can have also cold crystallization here. So in addition, Jean-Marie's group also investigated the cooling, the crystallization peaks, and also the crystallization enthalpy versus the cooling rate, and could see that in different PVDF PMMA content, you had some beta phase which here even at 5% of PMMA, which was very interesting as a result. And of course, the DE system shows that with PDF, which is the black one, of course, you have a ferro system, but when you add more and more PMMA, you can see that you have some file going to piezoelectrical system. And at only 5%, the remanent polarization is already very high, showing that indeed it's not so important to add a big amount of PMMA in your system. So 5% PMMA is required to promote the Curie, and they show that you have a very strange tendency from polytrifluoroethylene to 100 point up to 180 about 70, and the Curie temperature, of course, is lower than that melting point. This was determined by DSC. Indeed, the system relies on the different intermolar layer in which the bulky trifluoroethylene is going to force to have some free action of distance of VDF, showing that L2 here is higher than L1 in which the crystallization can occur and favor the beta phase. So this was also revisited by Tashiro and Kobayashi. This is a very nice paper here in 1989, and even they revisit that in 2006. And the profile of melting temperature does not change from what observed Yagi and Tatomoto on the slide before. while the crystallization temperature also is ranging more or less in the same tendency, and the ferro, the Curie temperature change a little bit according to you cool it or you melt it. So you can have a different non-significant amount of difference between the process you use in order to have different Curie temperature. At the beginning of my presentation, I mentioned that it was possible to show a different tendency of the polymorphism according to the treatment you use on your film. So this chart represents the DE curve regarding a high pressure crystallite PVDF, so which is more kind of ferroelectric behavior, and compared to uniaxial stretch PVDF at room temperature. So it can be a little bit slimmer. It's not yet piezoelectric, but it's much better profile than when you make a high pressure crystallite system. And the same group also investigated the thermal stability and also the residual piezoelectric activity here. So you can see that you have, according to the conditions used, for instance, when your film is poured with AC electrical field at room temperature, and then direct current field at high temperature, you can have some different behavior. So this is the piezoelectric activity versus annealing temperature. Of course, the film has to be annealed in order to enhance the properties. So I would like also to mention a nice work from several groups regarding the cross-linking. And Katja Luce in Groningen did the radical copolymerization of VDF with vinyl acetate, which was then hydrolyzed into vinyl alcohol. So you have a copolymer in which the blue balls are VDF, and then you have some vinyl alcohol incorporated here. And of course, from the alcohol, you can make some cross-linking with hexamethylene diisocyanate in order to prepare a cross-link system. So you are between interchange, you have HMDI, which occurs. And these are physicists group, so they measure, they study the DE parameters, and they show that without any cross-linking, you have a kind of system, while as soon as you increase 5% HMDI or 1% HMDI or 20% HMDI, you have different profile, even going to kind of electrical behavior. Another point which is very important regarding the beta phase, so I'm a little bit out of the topic today, but I would like to mention that Lanceros Mendes in Spain has investigated a lot PVDF and copolymers of VDF and involving in lithium-ion batteries. And the presence of the beta characteristics influences a lot the capacity of retention at 20 Celsius. So this is very important. And in the case of VDF trifluoroethylene, which is a beta phase, you can get a very high capacity compared to PVDF HFP or PVDF itself or polymer containing VDF and chlorotrifluoroethylene. In the lab, probably Thibault remembers very well his PhD. We try, in collaboration with Arkema, we try to figure out if it was possible to have some piezoelectrical system, even better properties, adding a third monomer. So one key reaction was the copolymerization of annealing fluoride with trifluoroethylene and this acrylate acrylic acid, which has a CF3 group. The CF3 group inhibits the homopolymerization of this monomer. And as I mentioned before, the radical initiator enables to lead to terpolymers composed of VDF trifluoroethylene. So the reaction was monitored by Fluoride NMR. I go very fast because probably you're not too familiar. So interestingly, you have a very wide chemical shift in which you have a CF3 signals assigned to MAF. Then you have a CF2 assigned to VDF and to trifluoroethylene, and then the CF characteristic of the trifluoroethylene. And what is very interesting is the MAF reacts very well with VDF, and then when it's totally consumed, VDF is going to react with trifluoroethylene. So the presence of CO2H enables to make some addition, And these charts represent the two comparison of addition of this copolymer compared to that of VDF and trifluorine, so meaning that you don't have any math. You can see that here the film is peel off, so you make the test system, and while here when you have a terpolymer with 1% only of math, you have a very good addition. And this good addition enables to have some layers of gold electrodes. And as you can see here, you unfortunately you don't have the piezo electrical system, but this is a ferro. The curve regarding the content of CTFE, and as you can see, the higher the content of CTFE, the slimmer the tendency, showing that you go to piezoelectric system here. Very fast because I speak too fast. So this paper also corresponds to the investigation of electrical energy versus electrical field. And as you increase the content of CTFE, you're going to increase electrical energy here, so 0, 4, or 8. And this is the same for the mechanical energy. And also the K2, which represents a kind of electromechanical coefficient, shows some lower compared the coupling coefficient compared to the copolymer. So the last point I would like to mention is another work of Katja Luce in Groningen. Her group enabled to make some tri-block copolymers by first-degree polymerization with a peroxide, peroxide carbonate, using VDF and trifluoroethylene. Chemical modification of a CH2Cl into azido group, and then click chemistry onto some alkene containing polystyrene or polyvinyl pyridine, showing that in certain of the tri-block copolymer is very active because you can have very nice electroactive properties. And finally, the last one is a mixture of terpolymer based on VDF, trifluoroethylene, and chlorofluoroethylene. So this is another terpolymer sold by Arkema, making a blend in PVDF at about 180 to 100, and oven and then quenching here. They observe that the directive constant is rather high when you increase the terpolymer, okay, and even 40% is very high, while the loss tension is not so critical according to this terpolymer. So the DE shows that again with PVDF you have this piezo ferro behavior, and it's getting slimmer and slimmer as soon as you increase the content of the polymer. Just to mention that PVDF is a very interesting polymer. It's light, processible, thermal, and chemically stable. But more and more new VDF containing copolymers or terpolymers have been used. Alpha phase can be enhanced from PVDF if some chemical processing or pressure processing or thermal processing are investigated, or even adding some polymers or fillers. Don't forget that architectures can be very useful in order to prepare some attractive systems with piezoelectric properties. And indeed, and this will be my conclusion, in order to work in this very fascinating area, we need the cooperation between chemists, physicists, and researchers involved in morphology, processing, assembly, and of course, end users. Thank you very much for your kind attention. This is a slide about all the different. I would like to thank Thibaut, of course, Celestin, Vincent Ladmira, Gilles Silly, who helped us a lot for NMR, Leizu, with who we had a collaboration, and of course, professor in Japan, in Rincon. I want to thank Arkema company, French National Agency, TOZO, for the math compound, and this is a French fluoride network. Thank you very much for your attention. If you need more information, please refer to this information. Thank you.